All right, so we're going to start chapter 8 today. And chapter 8 is all about applications of the integral. Okay, and we're going to start by looking at areas and volumes. Now, you already understand the integral as the area under a curve. But we're going to show some variations today on the traditional way of finding the area under a curve. And we'll start with this example 1, where we have a triangle with a base of 3 and a height of 6. Now, you know how to figure this out. You know how to find the area of this triangle, right? Area is just 1/2 base times height. So if we take 1/2 times the base, which is 3, and the height, which is 6, we get 9. Okay, so it doesn't have any units on this, but so the area is 9 units, square units of whatever the units are. And but now we can use that to check our work for the areas that we're going to find using the integrals. Okay, so it's kind of handy to just do a simple example first, and then we'll get into some more complicated cases. All right, so this part B just looks exactly like the integrals that you're used to. We're finding the area under a curve, the area between the curve and the x-axis. Okay, and so you understand an integral is the limit of the Riemann sums, and so we can slice this area into these little rectangles where the width is delta x, and the height is just the value of the function, right? So this is just y, and in this case y equals 2x. So if we want to find this area, then each slice has an area of basically y times delta x, right? And then y is equal to 2x, so we get 2x times delta x. And then if we sum up all those little pieces and take the limit as that delta x goes to 0, or the number of slices goes to infinity, is how we usually put it, we end up with an integral. So we have the integral from 0 to 3, right, because we're integrating the base across the base of 3, of the length, which is, or the height, oops, I'm getting ahead of myself here, the height of this rectangle, which is 2x, and then this delta x becomes dx. Okay, so you can think of this as being the height, and essentially this dx is there to represent the width of each of the little slices. And okay, we can do this. So that's just x squared, right? And we want to evaluate that from 0 to 3. And so when we put those values in, we just get 9, which matches what we were expecting. So that's pretty much the traditional, the area under the curve, just like we have been doing. But that's not the only way to use integrals. So I want to show you some different ways that we can integrate a function. And one of those ways is to look at horizontal slices. We can actually slice this triangle horizontally. So let's try out that method. So here we have a slice where, so this is delta y now, okay? And this essentially is, okay, so we're going over here. This is essentially x, but then, so then this is 3 minus x, okay? And so that the length of each one of those rectangles is 3 minus x, okay? If x is the value of the function. And so if you look at each slice, so each slice has an area, of basically, 3 minus x delta y. But now we're going to we've got delta y, so we want to actually integrate with respect to y. So let's rewrite this function as x equals 1/2 y. Okay, so then we get 3 minus 1/2 y times the width, which is, or the width of this little slice, which is delta y. Okay, and then again, we can think of it as taking out these little slices and just dividing the interval into more and more slices, and so then we get the integral. And in this case, we're going to integrate with respect to y. We're going to integrate from 0 to 6. Okay, so because we're taking these horizontal slices instead of the vertical ones. And then the length of each slice then is 3 minus 1/2 y, right, dy. Okay, so this represents the length of the slice, and then this is basically the width. All right, so let's do that. We can do that. We can integrate this function. We get 3y minus 1/4 y squared. Okay, because the integral of y is 1/2 y squared, but then we already have a 1/2, so 1/2 times 1/2 gives you a 1/4. And we're going to evaluate that from 0 to 6. And let's see what we get. So let's plug in. We get 3 times 6, which is 18, minus 1/4 of 36, basically. 36 over 4, which is 9. And then, so 18 minus 9 is 9. So either way, we get the same result in all these cases. So mostly just to help us verify that, okay, our thinking is correct about how to do this. So that's just an example of a different way to apply integration to finding areas in the non-traditional way, right? Where we're just trying to find the area between the curve and the x-axis. So we'll continue talking about these alternative ways of using the integral in the next example.